Good afternoon, everyone. Welcome to my presentation. I'm Kangming Lee. I'm a postdoctoral fellow working with Professor Jason Hatcher-Simper at the University of Toronto. And today I am very happy to present some of the recent work of our group in the AI-driven research in material science. So, long story short, the work that I will be presenting today is centered on two aspects of machine learning application, which concern human bias and the volume of data. So here are my questions. We all know that human bias can exist like in data generation, the analysis of the data and the model training. Then how can we use machine learning to remove such bias in the data analysis? And if there is already a bias in our data, how can we get over it by combining the state-of-the-art neural network with big data? And speaking of big data, big data always imply big knowledge. How much more information can we extract from the data we already have, and how can we maximize the amount of information extracted from our data so that a small amount of data can be as useful as big data? So in the following, I will speak about 4 case studies on addressing human bias and maximizing the knowledge extracted from data. 2 of them concern experimental data analysis and are performed by my colleague. The other 2 are focused on computational data and are done by myself. So the first case study performed by Renze, a PhD student, concern electrochemical impedance spectroscopy analysis. EIS is a characterization method widely used in electrochemical analysis by applying a small perturbation on the system and measuring the correspondence response. We can obtain the information of the system through the impedance spectrum. Typically, the EIS data is interpreted using equivalent circuit model. However, building such ECM model is very challenging because it often requires an expert level of knowledge and can be time-consuming and also subject to the overfitting and human bias. In fact, there are an infinite number of possible ECM that can fit the experimental data very well, but are not necessarily physical. And also, the EIS data analysis is also an example where we have abundant data, but we don't need to train a neural network. What is important here is rather a physically reasonable, interpretable, and simple circuit model. So in this study, Renze developed a package for the automated EIS data analysis for the ECM generation and provide enhanced physical interpretation using the statistical tool. So here is the workflow of its algorithm. First, the EIS data are imported, and then the outliner are removed in the processing, and next an evolutionary algorithm is used to generate the potential ECM solution. Non-physical ECM solution are removed in the post-filtering, and then the Bayesian inference is used to explore the probability distribution of the ECM parameter. Some further statistical checking is performed, and finally a statistical optimum model is suggested. So here is a case study for the OER electrocatalysis. Two ECM solutions are presented here. On the left is the statistical optimal solution suggested by our algorithm. On the right is the solution initially proposed by our expert. For each of these two solutions, we show the circuit structure, the probability distribution of the component value, and also the fitting quality of the EIS spectral data. First of all, judging from the R2 score, we can see that the fitting quality are actually quite close between the two solutions. But we also need to consider the complexity of the circuit structure to avoid the problem of overfitting, right? So here, clearly the solution suggested by our algorithm has a simpler structure. This can also be seen from its lower AIC score, which indicates a better balance between the accuracy and the complexity of the model. Furthermore, the statistically optimal solution has a relatively narrow and Gaussian-shaped distribution of the component value, which are statistical preferred characteristics and may be also more physically reasonable, whereas the distribution of the expert solution is broader, has an irregular shape, for example here, and also have some divergence, meaning that you can have equal probability for different component value. So here is so this is the result for this case study. The second case study is about maximizing the information extracted from the SEM image of membrane. Membrane are vital material in many applications, but their characterization is largely limited to the 2D imaging technique, which do not provide directly the 3D spatial arrangement and the connectivity of the membrane. On the other hand, 3D imaging technique is expensive and time-consuming and also not always accessible. To address this bottleneck in membrane characterization, Human, another postdoc in our group, used machine learning to develop a package for the reconstruction of the 3D membrane structure using a single 2D micrograph. A key aspect in his work is to extract the feature from the 2D image. Here, for each image, for each segmented image, we first calculate a distance map for the solid phase and the void phase by calculating the distance of each pixel from the nearest phase boundary. After having this distance map, we can then construct the histogram of the distance and obtain this histogram. And finally, we can combine the two histograms into a single distance function, which is found to be able to capture the statistical distribution of the solid phase and the void phase in the membrane. So here is the workflow of his algorithm. First, a 2D image is randomly selected from the experimental image dataset of a given membrane and segmented, and then a combined distance function is extracted from this image. And then in the next step, a 3D structure is randomly initialized and a random slice is selected from it and a combined distance function is obtained similarly. The two distance functions are then compared, and a Bayesian optimization is used to update the reconstructed 3D structure. And through 150 iteration, the algorithm could successfully find the optimal 3D structure within a few minutes, compared to a month of optimization using the 3D imaging technique. So here is a comparison of the original membrane and a reconstructed structure. Clearly, the two structures are not completely identical, right? But they are actually statistically similar. To show this point, we first compare the overall property of the membrane, including the pool radial distribution and the throat radial distribution, and also the coordination number distribution. All these three distributions show remarkable similarity between the original and the reconstructed structure, especially considering the fact that here we are only using one single image for the 3D reconstruction. And in this table, we provide a further quantitative comparison for several key parameters affecting the membrane performance. We can see that the reconstructed morphological parameters are quite similar between the reconstructed and the original one. On the other hand, we can see the error of the permeability is somewhat larger. In fact, this is because this is a transport property obtained from computational fluid dynamic simulation, and it is a highly sensitive property to the membrane structure. But I would say with the overall group agreement, this proof of principle study demonstrates the feasibility of the 3D reconstruction using a single image, and we believe future development can help further improve our algorithm. So, so far we have been discussing the experimental analysis, and in the next two case study, we will turn our focus on the computational data. Compared to the experimental dataset, computational dataset tend to be larger, containing up to millions of data points. The recently release of Open Catalysis project contain even hundreds of millions of data points. Despite being very large, this dataset may be biased toward the interest and the mission of the database developer. The community benchmark, on the other hand, is often based on the traditional cross-validation, so they cannot reflect the database bias and can also lead to overconfidence in the machine learning model. So if we train a model using the data we already have today, one question is that will it be able to predict the property of future material? Or to put it in another way, if we take a model pre-trained on the data set we have a few years ago, how well can that pre-trained model predict the new data in the current data set? So here we perform such a case study on the formation energy prediction of the metallic alloy. In this study, we have looked at both the neural network and traditional machine learning model, but in the following, I will only talk about the performance of the neural network for simplicity. So we use a neural network called the Align model. The Align model has achieved a state-of-the-art performance in several tasks in the community benchmark. For example, the Align model has an excellent performance on the Material Project 2018 or MP18 with a very small mean absolute error and a very good R2 score. So we take this pre-trained model and we test it on some of the new data in the MP21. So the first figure here shows the Align model prediction versus the ground truth. The disagreement for some new data is clearly striking and unexpected. And the second figure here shows the similar thing, but for the prediction error as a function of the ground truth. A considerable portion of this error vary from 1 to 3 EV per atom, much larger than what would be expected from the cross-validation MAE here. Also, considering the very low R2 score on the test data, one might argue that a state-of-the-art model trained on biased dataset may be just as good as a random guess for if you are using it for some test data. So after some digging down, we find that the poor generation performance is related to the imbalance structural type in the dataset. In this figure, we show the number of structures as a functions of the space group in the training and the test data. We can see that the distribution of the data is highly imbalanced, and many space groups have few training data. And the second figure is a scatter plot of the prediction error on the test data for different space groups. One can see that larger error are associated with the space group 71, which have few training data. However, this isn't the whole story, because you can see that the space groups 38 also have few training data, but they are well predicted. In fact, we cannot reason using a single feature like the space group. So what we do next is to use a UMAP, a dimensionality reduction technique, to project the high dimensional feature space onto a 2D dimensional plot. So the UMAP plot here clearly separates the test data into two clusters. And when we further plot the training data on top of the test data, we can see that the cluster with low prediction error is actually well covered by the training data, whereas the other cluster with large prediction error have no training data. In other words, we can identify the blind spot in the feature space and foresee where the model may be inaccurate. So now we know that. Now that we know the blind spot, we can use this knowledge to guide the data acquisition, right? So the idea is that we know the weakness of our model, and we try to improve its prediction robustness by including a minimum amount of the test data into the training set. So in this figure, we show the prediction error on the test data as a function of the number of newly added training data. And the top of the X indicates the proportion of the added data with respect to the whole test data. We try several active learning algorithms, and all of them allow to significantly decrease the prediction error with only 1% of new data added. In other words, we don't need to include all the new data in the MP21 in order to solve the performance issues, but only 1% of new data. So knowing the blind spot is very important to efficiently to efficiently build and expand our dataset. On the other hand, this study clearly suggests that there may be many redundant data in our material database. Is that really true? Is the redundancy a widespread issue across different material dataset? And how serious is the degree of the redundancy? We don't actually find the answer in the literature. Possibly because people simply take all the data they have to train the model, but actually there are also now also indication that the material data are becoming too big for training the neural network, and the issue of redundancy only make this situation worse. So to find out the existence and the degree of data redundancy, we performed an extensive examination across multiple large material property and data set, and using different machine learning model. And I will show a few representative cases in the following. We in this study, we first perform a random splitting of the whole data set into two parts to obtain the full training set and a holdout test set. Then we use a pruning algorithm to select informative data and remove the uninformative one into the training set. So we start from the full training set and then gradually reduce the training set size by pruning the uninformative data, which becomes unused data in this figure. So here is the model performance on the holdout test set as functions of training set size, which is expressed in the percentage of the full training set. Each figure here represents the results for one material property dataset, and only the results using the XGBoost model are presented, but we also examine other models and the results are similar. And the first thing to notice is that the training data selected using the pruning algorithm lead to better model performance than the data selected using the random sampling, which is not surprising, right? So the pruning algorithm is found to be very efficient in selecting the informative training data. We can also see here that using only 30% of the full training data here can train a model with little performance loss compared to the full model, the model using the full training set. And here we see the similar thing is around 30% of the data. And for the bandgap prediction in the OQMD dataset, even 10% of the data is sufficient, which is very surprising. So this means that we can remove like 70 to 90% of the training data without really damaging the model performance. Why? To better understand this issue, we also test the model on the unused data that are removed from the training set. So here we make a comparison of the R2 score on the unused data and the holdout test set. We can see that the model predicts this unused data, this informative data very well, and their predictions are much better than those of the holdout test set. For example, for the formation energy prediction in MP21, the model trained on 30% of the data can predict the unused data, and namely the other 70% of the data very well with an R2 score of 0.995. This means that the informative data are actually the data that are well predicted by the model, and therefore they are indeed redundant. It is not surprising that increasing the size of the training set does not improve model performance, because there is a little new information to learn from the well-predicted data. It should be pointing out that our pruning algorithm itself is not an active learning algorithm, because the information of the label is used during the pruning. So we attempt several uncertainty-based active learning algorithms to see if we can approach the performance of the pruning algorithm. And we find that it is possible. And the green line here are the results of the best active learning algorithm we have tested, namely the query by committee, which quantified the prediction uncertainty as a disagreement between different machine learning models. So we can see that this algorithm actually allows us to use like 40% of the formation energy data, or even 10% of the band gap data, to obtain a model performance similar to the one using the full training set. So to summarize, machine learning tool can help us to remove human bias and provide a statistical enhanced physical interpretation in the EIS data analysis. We show that the dataset bias is presented in computational dataset, and we cannot overcome the resulting performance degradation on the out-of-distribution sample, even using the state-of-the-art neural network. So never trust a model without examination, and trust even less the model with a similarly excellent performance. We also probe into some question around how much data do we really need, and I would like to leave that as open. In our case, we showed that it is actually feasible to reconstruct a 3D membrane structure using a single SEM image instead of 400 image with a good accuracy, and it is also feasible to use 10 to 30% of the data we have in some case to train a machine learning model with little performance loss. And in the end, we would like to thank our key collaborator and the funding agents. Thank you very much.
Thank you very much. Very interesting talk. There is some question in the room. It's coming. We need to bring the microphone to the person who will ask the question.
Dr. Lee, this was probably the most interesting presentation that I've seen combining Bayesian inference and electrochemical impedance spectroscopy. So it was really, really nice. I enjoyed it thoroughly. I have a few questions on that oxygen evolution reaction use case that you presented. What is the situation that you analyzed? I mean, is it free corrosion? In which case, what was the metal surface reaction that was explored, the counter reaction? Second one is the oxygen reaction itself goes through multiple pathways. Have you had any multiple reaction situation analyzed through your Bayesian techniques? And also, a third question would be, what is is there you've said, since you're using a Bayesian inference, what is the prior knowledge that you're putting in the model?
Okay, thank you for your question. Because I'm not actively participating in this work, I cannot say I cannot respond to your question precisely. For the initial distribution probability, the prior, I know that they are using a random they initialize the probability as the uniform one. But for other questions, I'm sorry that I cannot reply to your question, because this is not done by myself. But I would like to I will ask this question back to my colleague. Thank you very much, and I'm sorry I cannot I don't have the ability to respond to all these questions.
Thank you. Any other question? Okay. Oh yes, there is one question here, so just wait a minute.
Thank you for your talk. The question is, how do you evaluate the quality of active learning? So if you have a fixed data set, for example, and you have some kind of active learning algorithm, how can you actually is there any metric that you use to evaluate the quality of sampling new points when you actually don't have the access to the estimated function? So you have a data set that is already collected from the underlying function.
I would say that after doing this analysis, the idea to estimate the quality of the active learning is that initially we build we can build a holdout test set by randomly sample the data from the distribution we want to explore, and then we take this data as the test set, and then we perform active learning. And when we do the active learning, we can also have another test set which is not holdout, but another test set which is also randomly selected from the distribution we want to sample. And we use that kind of like the validation test set to guide the active learning process, and to see up to which point we can stop our active learning algorithm. And after all this, we can take our training set, the final training set, and finally to use it to test our test set to see if we are really capturing the property of the distribution we want to sample. Yeah.
Thank you.
Thank you. So I think it's time to thank the speaker. So thank you a lot, Dr. Lee, and thanks all the speakers of the session.
Thank you.